Greetings, everybody. So once again, in this problem, we are asked to find the area of the surface generated when the parametric curve x is equal to 3 cosine cubed, y is equal to 3 sine cubed, with t running between 0 and pi over 2, is rotated around the x-axis. So just to remember, again, kind of motivating where that formula actually comes from, when we have a curve, any curve, and we're rotating that curve around the x-axis, then we're going to end up with a shape that basically looks something like this. And so when we want to kind of find the surface area of that, we imagine taking infinitesimal strips. And the infinitesimal strips are all going to be of width ds. And then the length of those strips is then going to be the circumference of the strip that we have. Well, the y value, or the radius for that strip, is really just going to be given by our value y. And so the surface area is going to have a formula of the integral over the curve gamma of 2 times pi times y. So this gives us the circumference, and then times the length, or the width of our strip, ds, being the arc length element. So for the arc length, we remember that that has a formula of the square root of the square of dx dt plus the square of dy dt dt. So if our function has an x value of 3 cosine cubed, then our dx dt is going to have a value of 9 cosine squared times sine of t with a negative sign. Likewise, if y is going to be 3 sine cubed of t, then our dy dt is going to be given by 9 sine squared of t times cosine of t. If we take our dx dt and our dy dt and then plug them into our differential form for arc length, then this is going to give us the square root of a minus 9 cosine squared t sine of t squared plus a 9 sine squared of t cosine of t quantity squared dt. Well, expanding these powers, what we then have is we have an 81 cosine to the fourth of t sine squared plus an 81 sine to the fourth t cosine squared of t square root of that dt. So in this, we can factor out an 81 cosine squared t sine squared of t to then give us a cosine squared t plus a sine squared t underneath the radical. Well, the cosine squared plus the sine squared becomes 1, and so kind of looking over our interval, 0 to pi over 2, cosine is going to be positive, sine is going to be positive, so when we take the square root, we just end up with 9 cosine of t sine of t dt. And so this one now we're able to put back into our formula for our integral. So in our integral, we're going to have the integral from 0 to pi over 2. We have a 2 pi and then y being our 3 sine cubed t, and then our ds being given by 9 sine of t cosine of t dt. So cleaning this up, a little bit, what we then have is the integral from 0 to pi over 2, 54 pi, and then we've got a sine to the fourth of t cosine of t dt. So for this, we can do a u substitution. If we then let u equal to sine of t, then our du becomes cosine of t dt. And so what we would then have is a 54 sine to the fifth of t divided by 5, and that evaluated between 0 and pi over 2. So here we end up with a final answer of 54 pi over 5 sine to the fifth of pi over 2 minus a sine to the fifth of 0, or just 54 pi over 5. So I hope you've enjoyed this. I hope it's been informative, and I will see you guys in the next example.